Welcome back. Continuum mechanics is concerned with deforming and flowing continuous materials, i.e. solids and fluids. The key quantities of continuum mechanics include stress, strain, and rate of deformation, which are all tensor quantities. As we discussed earlier, continuum mechanics applies at scales where the densities of physical quantities such as mass, momentum, and energy can be approximated by continuous or piecewise continuous functions. And as a result, the governing equations become partial differential equations, functions of x, y, z, and time. The conservation laws of continuum mechanics, the conservation of mass, momentum, and energy, are universal. They apply to all materials. But to describe the mechanical properties of particular solid or fluid materials, we also need a constitutive law. This is a mathematical equation for the stress as a function of a kinematic variable such as strain or rate of deformation. It must usually be determined experimentally. Let's start by looking at the concepts of stress and strain in one dimension so we don't have to worry about the fact that they are tensors. Stress is a tensor that represents the forces of interaction in a continuum across surfaces. Therefore, stress has units of force per area. So let's consider tension applied to this cylindrical sample with cross-sectional area A with forces normal to that cross-section Fn. The normal one-dimensional stress sigma in this one-dimensional example is Fn divided by A, and this is a so-called tensile stress. Strain is a tensor that represents the change of shape, i.e. lengths, in a continuum. So if our sample had an original length of L0 and as a result of the application of the forces stretched to a new length L0 plus delta L, then the 1D normal strain in this tensile example, epsilon, equals delta L over L0. So stress is force per unit area, strain is length change. Now, there are other kinds of stress. For example, shear stresses arise from forces acting tangent to surfaces rather than normal to surfaces. So if we imagine forces acting tangent to these surfaces with area A, then the shear stress in this example, tau, is Ft divided by A. Again, with units of force per area, but now it's tangent forces per area. Shear strains describe the angle changes associated with deformation of a continuum. These actually require length changes too. For example, if the angle change produced by these shear stress in this example was theta, then the so-called engineering shear strain gamma would be the tan of the angle theta, or theta for small angles. If instead of thinking of this situation as a deforming solid, we think of it as a flowing fluid with the velocity of v on top and minus v on bottom, and a gradient of velocity with respect to the y-axis, then the shear rate in this fluid flow example would be that gradient, dv dy. It's the rate of shear strain. So let's look at constitutive laws. Constitutive laws describe the mechanical properties of a material and are so named because they depend on the constituents of the material, what the material is made of. They are a mathematical relation for the stress, such as sigma, as a function of the strain or strain rate or some other kinematic quantity. The constitutive law is always an idealization and an approximation, and the validity of this approximation depends not only on the material to which you're applying it, but also the conditions under which the material is being loaded. For example, under working loads, a material might be well approximated by one constitutive law, but under loads that would cause it to fail, a different law would be needed. The constitutive law must typically be determined by experiment. Its form and parameters are constrained by conservation of mass and energy and thermodynamic considerations. And the choice of the form of the constitutive law should ideally be based on considerations of the microstructure of the material. The two major classes of continuum material are solids and fluids. Solids, on the left here, can support a shear stress indefinitely without flowing. They assume an unloaded natural state and can deform with minimal energy dissipation or with substantial energy dissipation. They are often composites, meaning they're comprised of different materials types. Fluids are liquids and gases. Gases have lower density and higher compressibility than liquids, and there's usually a phase transition as a function of temperature and pressure from liquid to gas and gas to liquid. They can support a hydrostatic pressure at rest, but they cannot support a shear stress without eventually flowing. They have no unique unloaded shape, so they fill their container. Liquids tend to have a free surface, whereas gases fill the entire container, and they dissipate energy as heat when they flow. In the same way that solids are usually composites, fluids are usually mixtures. So one of the commonest constitutive models is the elastic solid. Let's consider again our uniaxial sample subjected to normal stress sigma, resulting in strain epsilon. In an elastic solid, the stress is a function of the strain and only the strain, so sigma is a function of epsilon. The work done during loading is stored as potential energy, and upon unloading, the potential energy is released in a reversible process, and the material returns to its original, unique, natural state. If we measure the stress sigma as a function of the strain epsilon in many common elastic solids used in engineering, then we often get a straight line, and the slope of that line, E, is called the Young's modulus. A material that satisfies this stress-strain relation is called a Hookean or linear elastic solid. However, many tissues and materials in biomechanics have a non-linear relationship between the stress and the strain, and therefore the Young's modulus depends on the strain, and we call it the tangent modulus. So this is an example of a non-Hookean elastic solid. A common constitutive model for fluids is the viscous fluid, in which the shear stress tau is a function of the shear rate gamma dot. For example, in a Newtonian linear viscous fluid, the shear stress tau is proportional to the shear rate, and the constant of proportionality mu is called the viscosity. Viscosity is the resistance to shear, and work done in viscous flows is dissipated as heat. A viscometer measures the viscosity by measuring the torque required to rotate a disc above a stationary plate with a layer of fluid on it. A viscometer creates a type of flow called a Couette flow, with a linear gradient of velocity from 0 on the bottom to some finite value on the top, and the gradient of this velocity is the shear rate. And by measuring the force or torque required to produce that motion, the shear stress can be computed, and thus the ratio of the shear stress to the shear rate is the viscosity. This plot shows blood viscosity as a function of shear rate for different hematocrits, which is different amounts of red blood cells. You can see that plasma, where there's no red cells, is Newtonian. The viscosity doesn't change with the shear rate, it's constant. However, whole blood, which has about 45% red cells, has a non-constant viscosity which decreases with the shear stress. So whole blood is a non-Newtonian shear thinning fluid. A more complicated class of material that's commonly seen in biomechanics is a viscoelastic material in which the stress is a function of both the strain and the strain rate. Viscoelastic materials combine elastic or spring-like properties with viscous or syringe fluid-like properties. They exhibit behaviors such as creep at constant stress, so their length doesn't remain fixed at a constant load, and they relax at constant strain, so the amount of force required to hold them at a constant length decreases over time. We can construct various different viscoelastic models by combining solid-like and fluid-like behaviors in different combinations. For example, if we put a solid and elastic material and a viscous fluid in series with each other, we get a Maxwell fluid. If we put them in parallel, we get a Voigt solid, and if we have two solid-like materials, or if you like, a Maxwell fluid in parallel with a spring, we get what's called a Kelvin solid or standard linear solid. So you can think of each of the syringes as representing a fluid with viscosity mu, and each spring as representing a elastic solid with Young's modulus E. So depending on the way that these properties combine, we get different behaviors. These graphs show what happens when a constant force is applied to models like this and then removed. In a Maxwell fluid, you can see that the spring instantaneously stretches, so there's an immediate deformation of the material. But then, because there's a syringe, a fluid-like behavior, the force will continue to pull that syringe out indefinitely. In other words, the material will flow. And then, when the force is removed, the spring will recoil, but the syringe won't go back, so it won't return to its original natural state, and that's what makes the Maxwell model more like a fluid than a solid. In the Voigt solid model, when the force is applied, initially nothing happens because it takes a finite amount of time for the syringe to start to stretch out. And as it does, it stretches the spring, which therefore slows down the syringe. As the force is removed, then the spring gradually brings the material back to its original state. So this is more of a solid-like behavior. A Kelvin solid is similar to the Voigt solid, except it has effectively an additional spring in series, with the result that when the force is applied, it instantaneously stretches, then it continues to creep like a Voigt solid, and then when it's unloaded, it instantaneously recoils somewhat and then creeps back to its original natural state. Another type of material behavior is called plastic behavior, and there are also constitutive models for plastic materials. Let's again consider the relationship between stress and strain in our uniaxial sample subjected to uniaxial tensile stress. As the stress increases, as the strain increases, but if we go too far, then we start to get some irreversible damage beyond a point known as the elastic limit or yield point. This is known as irreversible or plastic behavior, and if we unload before the material fails, then often that results in hardening of the material. This happens in metals a lot. On the other hand, if we keep loading, we'll ultimately reach a point known as the ultimate tensile stress and the ultimate tensile strain where we get failure. This type of failure is called ductile failure, and this type of plasticity is called a ductile plastic material. Another type of failure occurs in materials that are brittle. Soon after the elastic limit is achieved, the material fails suddenly, and this is called brittle failure, and such a material is called a brittle material. There are many other types of material behavior. Viscoplasticity describes the behavior of a material that acts like a viscous fluid, but only after the shear stress exceeds a certain finite yield stress. It takes a certain finite amount of stress before the viscoplastic material starts to flow like a fluid. Below that stress, it's a solid. And actually, whole blood is an example of this type of material. A thixotropic material, like the cytoplasm inside cells, undergoes what's called a sol-gel transformation from a gel to a liquid, similar to Jell-O that's partially set, and then you stir it up and it becomes liquid again. Strain softening, or the Mullins effect, is a property that's common to many polymer materials, including many biological tissues. This is a property where a material is permanently softened or softened for a long time after it reaches a new, previously unexperienced maximum load. So progressive, irreversible or nearly irreversible softening occurs, and example of this is a rubber balloon, which the first time you blow it up is much harder than the second and subsequent times. Here we see an example of successive cycles of loading and unloading in a biological tissue, a blood vessel, and we see several characteristics of many soft tissues. We observe that the stress strain curve is nonlinear and that the loading curve, the up curve, is different from the down curve. They create a loop called a hysteresis loop, and the area of the loop represents the dissipated energy. And this is a common characteristic of soft tissues. We also see that subsequent cycles of successive loading and unloading follow different curves that eventually start to converge to the same hysteresis loop. When the test becomes repeatable so that the nth test and the nth plus 1 test are not significantly different, then the material is said to be preconditioned. But it doesn't mean that when the material is preconditioned that there still isn't hysteresis. There can still be hysteresis once the material is preconditioned. So these are common characteristic properties of soft biological tissues. Next time, we'll review matrices and vectors in preparation for introducing tensors.